Chapter 12, Section 1, Characteristics of Gases. Okay.
The kinetic molecular theory describes the behavior of gas molecules and the physical properties of gases. The kinetic molecular theory views gases as being made up of large numbers of fast-moving particles that are far apart from each other. Most of the volume occupied by a gas is empty space. Gas particles are in continuous rapid random motion, and the forces of attraction or repulsion between them are essentially non-existent. Kinetic molecular theory relates the kinetic energy of gas particles to the temperature of the gas.
Okay, so let's talk about some of the properties of gases. So when you look at this, we're going to give a definition of the property, and then the bullets underneath that are going to be the postulates from the kinetic molecular theory that support this property. So property number 1 is expansion. Gases completely fill their container. Particles move rapidly in all directions is one of the postulates that support this, and there are also no attractions between particles. So if we think about this, if I have a container that's connected to a different container, one of them is filled with gas particles, the other one is not, and if I open the valve that connects them, we would see that gas particles would move from one container to another. So here's my container. This is my little valve that connects them. Here's all my little gas molecules. And so when this valve is open, all these gas molecules would flow into the other container, and they would expand to fill that second container. Fluidity. Gas particles glide past each other to flow. Now, gases are not the only ones that exhibit this behavior. I'm sure that when we use the term fluid, that most often what comes to mind are liquids. And again, this happens because there are no attraction between gas particles. The other reason why this occurs is because gas particles are so far apart. Okay. A really good example of this would come from the last chapter, or a couple of chapters back. If we think about chapter 8, we did the Ira Remsen demo, and so you probably remember the copper penny, the nitric acid, but let's talk about the gas. So we made this reddish brown gas, and we didn't want to let it escape into the atmosphere, so we let it flow from one flask to the other and then dissolve in the water. So this is a great example of fluidity that you're familiar with from class. Okay. Low density. Okay. The density of a gas is 1/1000th of a liquid or a solid. And again, it's because the particles of a gas are so far apart. Okay. Low density also tells us that the gas particles have to travel far distances before they can collide with each other. Okay. We're going to actually get a chance to look at low density in a couple of ways in the gas discovery lab that we're going to do at the start of the chapter. We're going to look at carbon dioxide gas, and we're going to look at water vapor. Compressibility. So the molecules of a gas can be pushed together and the volume decreased. Again, it's because the particles of a gas have such a large space between them. So if we look at two containers, one container here, and it's a flexible container, okay, and we put gas particles here. Okay. And then let's say I push down on this container and it crumbles to about half of its height. You can see that the gas particles are closer together. Okay. So we have decreased the volume, and we're going to see an increase in pressure. So this is one of the gas laws we're going to get a chance to talk about later in the chapter.
Gases differ from solids and liquids in that they expand to fill the shape of their container. Because there are large distances between gas molecules, gases have extremely low densities. Carbon dioxide, for example, is less dense than water, so bubbles of carbon dioxide rise to the surface. Gases are compressible to small fractions of their initial volumes. Because of this, large amounts of oxygen can be stored in tanks for scuba diving. Gases mix readily by diffusion. We don't have to stir or shake them to make them mix. Gases can escape containers through tiny holes in a process called effusion. This occurs when a bicycle tire is punctured.
Okay, so we have two more properties to talk about. Diffusion is the spontaneous mixing of the particles of two substances. Again, it's because particles move rapidly in random motion and the particles of a gas are far apart. It's also important to note that these particles are moving from areas of high concentration. So in other words, a place where there's lots of gas particles, to areas of low concentration. Okay. So think about things that have an odor: perfume, ammonia, vinegar. If someone opens a bottle of that somewhere in the room, eventually you'll be able to smell that along with the class. And again, it's because of diffusion. The area where the bottle's been opened is an area of high concentration, and where you are would be an area of low concentration. And it relates back to our earlier discussion of expansion. So you can see that I have two containers, one filled with hydrogen, one filled with nitrogen. When I open up the valve, they mix spontaneously. All right, so let's talk about pressure. Pressure is equal to force. Force is a quantity, and the unit for that is newtons, and it is per unit of area. Okay, so area would be length times width. So we know area would have units something like meters squared. So this would have units of newtons per meter squared, which we consider to be a derived unit. Okay. So instead of calling it newtons per meter squared, okay, we use other pressure units, which we'll get to in a second. Okay. Pressure is caused by particles of a gas colliding with the walls of its container, and it depends on volume, temperature, and the number of particles, which relates to the number of moles. So you're going to see as we travel throughout the chapter, we're going to talk about several mathematical gas laws that look at each of these relationships. And if we think about force per unit area, so think about walking through the snow. If I'm wearing high heel shoes, it has a little area. Okay. Same amount of force because it's still my body, but I have a very small area. Okay. And so I'm going to exert a great amount of pressure. So I'm going to sink in that snow. Okay. Let's see, I'm walking through the snow in snowshoes. Okay. They have a large amount of area, so it's going to give me a smaller amount of pressure, and I'll sink very little into the snow. Okay. So our atmosphere exerts a pressure. It's made up of gases, 78% nitrogen, 21% oxygen, and 1% of that is other gases. And so atmospheric pressure is the sum of the individual pressures of the gas. Okay. So some things you probably have recognized about atmospheric pressure, that the density of it changes as the altitude changes. So the closer you are to Earth's surface, the denser the air is. The farther you get from the Earth's surface, the less dense it becomes. Your ears popping is due to this situation. So your ears pop when the air inside your ear reaches the same pressure as the air outside. So let's talk about how we measure pressure. Okay. The device we use to measure pressure is called a barometer. Okay. And it was developed by Torricelli. So there's Torricelli. And it looks like this. So you can see from the picture that atmospheric pressure pushes down on the mercury in the dish. And this causes the column to rise. And then they measure the height of that column of mercury in the glass tube to determine what the atmospheric pressure is that day. Now here you can see on the screen it says it has 760 millimeters of mercury, but what you're probably most familiar with is inches of mercury.
A barometer is a device for measuring atmospheric pressure. The simplest type of barometer uses a transparent tube, usually glass, which is sealed at the top and filled with mercury. The tube is inverted in a bowl of mercury. When the air pressure is high, the mercury is pushed up the tube. When the air pressure is low, the mercury is lower in the tube.
Okay, so the average atmospheric pressure at sea level at 0 degrees Celsius, and so we talked earlier about pressure is force per unit area. It would have units of newtons per meter squared. And I mentioned the fact that that is a derived unit. Okay. So instead of using the derived unit, we use these units, millimeters of mercury, atmospheres, and kilopascal. Okay. Now kilopascal, this is really a prefix. The SI unit is really the pascal. Okay. And again, you can see that 1 pascal is the pressure exerted by a force of 1 newton acting on an area of 1 square meter. So it relates back to our discussion earlier of this being a derived unit. Okay. Okay. So the values I've given you here at the bottom of the screen, those are standard pressure values for the different units we're going to use throughout Chapter 12. These are the ones you're going to need to memorize. These are the ones we're going to use for converting pressure units, okay, which that's what we're going to do next. We're going to do some problem solving. Okay. So please note significant figures. So 1 atmosphere is 1.00. I have 101.3 kilopascals, 760.00. All of the zeros here are significant. 29.9 inches of mercury, and 14.7 psi, which is pounds per square inch. Okay, so before we get to our conversion factors for pressure and using them, let's kind of review what we know about dimensional analysis. Okay. So obviously I'm going to give you a problem. There's going to be a number and unit given to me in a problem. Okay. We're going to multiply by a conversion factor. We're going to put the given unit on the bottom of that conversion factor, and we're going to put the unit we want to know on the top. Okay. And then after we've plugged in the units, we're going to put in the numbers in our conversion factor, and those numbers make the numerator equal to the denominator. Okay. And just as a reminder, that 1 we put underneath our given unit is just a placeholder. It doesn't have any units. Okay. Right, and after all of that's done, we should be able to mathematically solve and get a number and the unit we wanted. Okay. Okay. So here we go. Here's my different units that I need to convert to solve. We need to get rid of the smiley face. Okay. We need to get rid of the sun. We need to get rid of the heart. We need to get rid of the cube. And the unit that I'm left with is going to be the diamond, which is the unit I wanted to have at the very end. Okay, so here we go. Here is our first problem. It says the average atmospheric pressure in Denver, Colorado is 0.830 atmospheres. We're going to convert from 0.830 atmospheres to the pressure in millimeters of mercury. So we're going to start with the number and the unit given to me in the problem. So here's what we're going to start with. I have 0.830 atmospheres. Okay. And we can put this over 1. Again, that 1 is just a placeholder, and it's to make everything look like a conversion factor. Okay. We're going to get rid of atmospheres. And the unit we want at the end is millimeters of mercury. So my answer is going to have units of millimeters of mercury. And then I'm going to plug in the numbers that we talked about on the previous slide. 1 atmosphere is equal to 760 millimeters of mercury. Okay. And we're going to look at all of the values in this setup to determine sig figs. So we can see that the least number of sig figs is 3. And if I multiply across and I round to just 3 sig figs, my answer is going to be 631 millimeters of mercury. Okay. All right. All right. Let's look at a second problem. So I still have 0.830 atmospheres, but this time we want our answer to have units of kilopascals. Okay, so here's my given. And again, we can put this over 1. That 1 doesn't have any units, it's just a placeholder. We're going to multiply by a conversion factor where I'm going to get rid of the unit that I was given, so we're going to get rid of atmospheres, and we want to know kilopascals. And we're going to use the conversion factors previously discussed. So 1 atmosphere is equal to 101.3 kilopascals. Okay, so atmospheres are going to cancel. The unit at the end is going to be kilopascals. And if we look at this problem, we can see that everything on the bottom is a 1. Okay, so we're going to multiply across. And again, we're going to look at all of the values to determine sig figs. So we can see that the least number of sig figs is 3. So the answer here is 84.1 kilopascals. All right, so at this point, I'm going to ask you to pause the video, and there are practice problems 3 and 4 for you to complete of your note outline. Okay, let's talk about our next type of problem that we need to learn to solve in this chapter before we can get to the gas laws, and that is one of temperature. Okay, so there are basically 3 temperature scales. The one you're probably most familiar with is Fahrenheit. It is not the one we're going to use in chemistry. Okay. Probably in a science class, what you most remember using is Celsius. Also not the unit we're going to use in chemistry class. But here's the relationship. So if I want to find the Celsius temperature, it is equal to 5/9 of the Fahrenheit temperature minus 32. So you're going to need to memorize this equation for your test at the end of chapter 12. Okay. The SI unit for temperature is really Kelvin. It has a symbol K, so there's no degree sign, it's just the K. The 0 point on the Celsius scale is designated as the freezing point of water. On the Kelvin scale, the 0 point is known as absolute zero. Okay. And it's important to note that 0 on Celsius and 0 on Kelvin are not the same temperature. Okay. Okay. So let's talk about how we convert from Celsius to Kelvin. So if I want to know the Kelvin temperature, we're going to add 273.15. And if I want to know the Celsius temperature, we're going to subtract 273.15 from the Kelvin temperature. Again, equations you're going to need to know for the test. Now, I mentioned that 0 Celsius and 0 Kelvin are not the same value. Okay, So you can kind of look at the temperature scales here and see Fahrenheit, Celsius, and Kelvin. You can see where the 0 Kelvin mark is negative 273.15 degrees Celsius. And it's important to note that if you go up 1 degree on the Kelvin scale, you're also moving up 1 degree on the Celsius scale. Okay. And we've already mentioned that 0 Kelvin is known as absolute zero. Okay. So STP is an abbreviation that stands for Standard Temperature and Pressure. You're going to see STP often throughout the problems in Chapter 12, so it's important to know what they mean. So standard pressure, it's referring to those values we talked about earlier. 1 atmosphere, 760 millimeters of mercury, 101.3 kilopascals. And standard temperature also refers to values we talked about earlier. It's referring to 0 degrees Celsius, and we know on the Kelvin scale that it is 273.15. Alright, so we're going to do a few conversion problems, and then there'll be some problems for you to practice. So let's start with converting between Fahrenheit and Celsius. So here's our equation from earlier. Okay. And we're going to plug in our temperature. So we're going to plug in 75 degrees Fahrenheit here. Okay. So we're going to subtract 32 and then multiply by 5/9. Okay. And since our measured value only has 2 sig figs, our final answer is only going to have 2 sig figs, and so we're going to get 24 degrees Celsius. Okay. In our next temperature conversion, we're going to convert from Celsius to Kelvin. Okay. So remember that Kelvin is equal to degrees Celsius plus 273.15. Okay. I'm going to plug in 1,535 degrees Celsius. We're going to add 273.15. And remember that when we add, it goes by the number of decimal places. So our given does not have any decimal places. My final answer is not going to have any decimal places. Okay. And the unit is just K. There's no degree sign with the Kelvin temperature. Okay. The expectation here is that I know it's an equation, but you need to show work, give an answer with correct units and sig figs. Okay, the last problem, we're going to go from Kelvin to Celsius. Okay, so again, Kelvin is equal to degrees Celsius plus 273.15. So we get 74.4 Kelvin is equal to degrees Celsius. Okay. So if I want to know the Celsius temperature, we're going to subtract 273.15. Okay. And again, if we look, our given has 1 decimal place. The value we're going to subtract from it has 2. The least number of decimal places is 1. So my answer should have 1 decimal place. So this answer is negative 195.8 degrees Celsius. Okay, so at this point, you are going to complete the temperature conversion problems 8 through 10, and that completes your outline.